Check it out now, y'all.
nanoHUB-U, online instruction.
So in this particular lecture, we're going to try to focus on a contact mode scan in atomic force microscopy. We're going to try to go through some of the important aspects of that scan, hopefully provide you with some background material that will help you execute contact mode scans a little bit more proficiently than maybe you would do if you hadn't gone through these lectures. To begin with, I guess the point we should make is that the purpose of a microscope is to obtain an image, and for the case of an atomic force microscope, that image is acquired in a rather roundabout and complicated way. It involves measuring the motion of a spring. In this case, the spring is a cantilever, as a tip is rastered across the substrate in a controllable way. And in particular, it's useful for you to remember that the image that you get in an atomic force microscope, that image is said to reflect the topography of your substrate, but what you're really mapping out when you obtain that image is the sample motion in order to keep the force between the tip and the substrate fixed. So when we talk about an image or when we talk about topography, we are really talking about the mapping of the Z substrate in order to keep the tip fixed, and that sample motion is then equivalent to the topography of the sample, and hopefully there's a close correlation between sample motion and topography. That's the whole point. So if you're doing a contact mode scan, right, your tip is in hard contact with the substrate, so there's an interaction force between the tip and the substrate, which is in the contact regime, and the instrument is going to do whatever it takes in order to keep that applied force between the tip and the substrate constant. That's the image that we obtain. There are many advantages of contact mode AFM. It's often a lot easier than dynamic AFM, and if you have any doubt about that, the second part of this course is focused on dynamic AFM and trying to understand what actually is going on when the tip oscillates above a sample. Contact mode AFM is a lot easier to understand. You can scan at a somewhat higher scan speed. It is possible to achieve atomic resolution on very flat samples using contact mode AFM. But it's also useful to scan rough samples with large changes in topography. That's sometimes easier to do in contact mode than in non-contact mode. There are a few disadvantages that we'd like to point out. In particular, contact mode scan will exert lateral forces on your sample. So if you've got loose particulates, those are going to be moved and pushed out of the way by the scanning tip. When you do a contact mode scan, you're going to be fighting this capillary meniscus force that we talked about earlier this week. That meniscus layer will form, and that will be part of an adhesive force that pulls the tip onto the substrate. And then lastly, you're probably going to have a reduced spatial resolution, so that you maybe won't be able to achieve the highest resolution possible with a contact mode scan. That's simply because the tip is directly in contact with the sample, and as you proceed to acquire an image, the tip radius will wear, it'll increase with time, and also you're going to damage softer samples, right? So that's something you have to worry about if you're going to execute these contact mode scans. I'm often amazed at the psychological barriers that students have in performing AFM experiments, right? Very often you need an expert operator to make the atomic force microscope work. It seems that Each sample requires a different cantilever and a different setup that you have to go through, so that realignment and readjustment procedure can be kind of tedious. AFM experiments just take time, and the results are often difficult to interpret in a meaningful way. So why bother, I guess, is the point. And even if an AFM contact mode scan is easier than a dynamic mode AFM scan, why make the effort to even try? And the point is that the information that comes out, there's no other way to get it. That's basically the point. So what we're trying to do is we're trying to lower these inherent barriers, these reasons why you would not want to do an AFM scan. We're trying to lower those barriers. And the way we do that is by understanding a little bit more what's going on, and possibly if you can replace these rote prescriptions that you have to memorize, if you can replace that with some understanding and knowledge, perhaps it'll be easier for you to engage in the practice of atomic force microscopy. I thought it would be useful just to list in an ordered way the different steps that you might execute if you're going to perform a contact mode AFM experiment. This is an overview slide. It's meant for you to look at on your own. There's no reason for me to read all these steps in sequence. But I thought it would be useful to at least have some ordered set of steps that you might follow if you're trying to perform a contact mode scan, possibly for the first time. So you can look at this list on your own if it's of useful. It might be of use to you. I will say that about 30 years of experience in this business has shown many, many times that good sample preparation is really the critical step in performing atomic force microscopy. And I'm constantly amazed at how often students will try to throw a sample in and obtain an image, and there's no prior effort to optimize the sample preparation or to even characterize the sample preparation. In my experience, this is a prescription for disaster. You'll be frustrated. The images that you get won't be very good, but it's a sort of lesson that you just have to learn by trying many, many times. And so if I can emphasize one point in this lecture that might make a difference, it would be to spend an inordinate amount of time in sample preparation, because this is a really crucial step in any AFM experiment. Sometimes students have a difficult time positioning the laser on the cantilever. Each company has each commercial company that makes AFMs has a different procedure. The one that I kind of like is an intuitive procedure, which basically starts at some point A, where A represents some initial arbitrary spot for the laser to be positioned with respect to the cantilever. The objective is to position the laser spot on the cantilever in a systematic way that requires minimal amount of effort. And one way that always seems to work is to first move the laser spot to the chip and locate the edge of the chip. That's at locations B and C in this diagram. After that chip edge has been located, then you can actually locate the base of the cantilever. That's at position D and E in this diagram. And then lastly, you can systematically move the laser beam so that it's at the end of the cantilever. That would be at position G in the diagram. So if you execute this procedure more than a few times, you'll become very proficient at it. It's not terribly difficult, and it allows you to reliably position the laser beam at the tip of the cantilever with a minimal amount of effort. Once the laser beam is positioned on the end of the cantilever, then you have to approach the substrate to the cantilever in a controlled way. And so I try to make the distinction between the position of the cantilever and the substrate, that's Z, and between the tip of the apex, and the substrate position, that's D. So Z is what you control experimentally. D is what's interesting in the physics and chemistry of the tip substrate interaction. And the point is you have to slowly change Z in order to make D on the order of a nanometer or so. And the way that's done is with a coarse approach. The steps of the coarse approach are shown in a schematic fashion in the bottom of this slide. Basically what happens is you slowly expand the Z piezo and look for a deflection of the cantilever. If no deflection of the cantilever is observed, then you quickly return the Z piezo to its original position, and then you take a coarse step, which is indicated by the downward blue arrow mark 3 on this slide. You then repeat that process over and over again in a stepwise fashion until finally your slow approach to the substrate produces a deflection of the cantilever, and at that point you terminate this process. This is the coarse approach process, and at that point your tip is then in contact with the substrate. After the tip is in contact with the substrate, you have to go through optimization of the feedback loop. And my experience has shown that this optimization process is really a sequence of successive approximations, and it requires you to tune the feedback loop in real time as you're actually performing AFM scans. Now, in order to do this in an efficient way, it's useful to have some broad perspective on feedback loops. And what I try to do here is I try to sketch in a very schematic way the essential features of any feedback loop that you're going to encounter when you use an atomic force microscope. Basically, what's happening is you're getting a signal from your AFM controller, which is the deflection of the cantilever Q. That deflection of the cantilever is in some way proportional to the tip sample separation distance D. And what you want to do is you want to maintain the deflection of the cantilever Q fixed with time. That implies a constant force between the tip and the substrate as you scan the tip over the substrate. The way that's done is by controlling that measured quantity to some fixed set point signal. That fixed set point signal in the case of contact mode scanning is the applied force that you want your tip to exert onto the sample. And by comparing those two quantities, Q, which is a measured deflection, and F0, which is your set point deflection or your set point force, right? You do that by basically subtracting your input signal from your set point to produce an error. And that error can vary in time, simply because the cantilever motion above the substrate is fluctuating in time, or it could be fluctuating in time. And what you want to do is you want to devise a control law that minimizes that error over time. And there are two prominent channels for this control law. One is a channel which is the proportional channel. It involves a constant case of P, and it multiplies that error signal by that constant case of P. It adds that signal to integral signal, which is indicated by the integral channel of the feedback loop. The integral signal actually integrates the error backwards in time, right? And there's a proportionality constant case of I that multiplies that part of the feedback loop. Those two quantities are added together and fed into a dynamic controller, which adjusts and produces an offset delta Z. And that offset delta Z then tries to minimize the difference between the deflection of the cantilever Q and the set point force F0. So the trick in this business is to efficiently and adjust case of P and case of I to optimize this feedback loop. And basically each channel in the feedback loop achieves two different purposes, right? The proportional controller allows the probe to follow the smaller, higher frequency features in the sample. And so by adjusting case of P, you're trying to optimize how quickly the cantilever can respond to small variations in topography. The backward integrator I call it backward because it's integrating backwards in time, right? That allows you to follow the larger low frequency features in the sample. And so by optimizing the parameter K sub I, it allows you to better follow the undulating features of the sample as you scan. Now, it's useful to have some understanding of how a feedback loop responds to a step change. And this is kind of the 0th level understanding of feedback loops that's often required to optimize feedback loop in an AFM. So I want you to consider a step change at some time t equals 0 to the for the signal that goes into the feedback loop. This is the input signal that goes into the feedback loop. That step change is shown in the bottom portion of this slide. The top portion of the slide schematically represents the response, the typical response that a feedback loop would have to that instantaneous step change. And in particular, there's a couple of features that are worth noting. The first feature that's worth noting is the feedback loop will not instantaneously respond to that step change. So there's going to be a delay time. Then there's going to be a ramp up or a slew rate that causes the feedback loop to send out a signal to try to correct for the step change that you input. That rapid increase often overshoots the optimal value by a certain amount. And once it overshoots, the feedback loop recognizes that and has to correct for it. So there tends to be an oscillation as the feedback loop adjusts whatever it's trying to control in order to match the input. And that oscillation would hopefully damp out in a short period of time such that the response of the feedback loop matches the input of the feedback loop after some sort of time, settle time that's indicated in this particular slide. So you might think, and in fact it's true, that if you could measure the actual response of the feedback loop to an input step change, that just from measuring parameters on this response curve, you could sort of automatically optimize the settings K sub P and K sub I that make the response of the feedback loop match the input signal as close as possible. And there are various algorithms or techniques that have been explained in the literature to perform that optimization. Perhaps the most famous one is this so-called Ziegler-Nichols Tuning Rule. This is just one example of the types of optimization procedures you'll find in the literature. This is a very old one. This goes back to the 1940s, I believe, right? And what the Ziegler-Nichols Tuning Rule says is that if you could measure the lag time and the rise time of your feedback response, then you can adjust the parameters K sub P and K sub I in a very simple way as indicated in this table. It's just related to the values of T sub L and T sub R indicated in this slide. This is just one example, but the trouble is, of course, when you're doing an AFM experiment, you never really have this nice step input, so you can never really measure the response to a step input in a systematic way. So it becomes very hard to measure T sub L and T sub R in the process of doing an AFM experiment, and so therefore it's kind of difficult to know how to adjust the parameters K sub P and K sub I. But nonetheless, in principle, you should be aware that this type of procedure is what you have to go through in order to optimize the settings K sub P and K sub I when you're taking a contact mode scan in atomic force microscopy. There's a few trends, a few systematic trends that are worth understanding and at least being aware of, right? So by increasing the constant K sub P, you tend to decrease the rise time you increase the overshoot, you have very little effect on the settling time, and you also decrease the steady state error of your feedback loop. And likewise, there's some guidelines for increasing the parameter K sub I. That tends to decrease the rise time, it increases the overshoot, it increases the settling time, but it eliminates the steady state error that's associated with your image. So one strategy that we like to use is that we tend to use K sub P to optimize the rise time. We try to use K sub I to better track the larger features in an image. So if you're scanning over a feature that's got a very sharp step associated with it, maybe that's best attacked by adjusting K sub P. You want the feedback loop to respond very quickly to that sharp feature, but you don't want it to overshoot and oscillate because that's going to produce spurious features in your image. There are many reasons why any particular tuning rule to optimize a feedback loop may not work, and usually it comes down to the assumptions that you're making are not accurately matched in the experiment, and the worst part of the equation is that you don't even realize your assumptions are not valid. So you're operating under false pretenses, basically. But it's sometimes useful to have some tuning rule in mind as you adjust K sub P and K sub I. If you do this, then you at least have a systematic approach to it. But don't be surprised if you apply that rule to a different sample with a different cantilever with a different spring constant and it doesn't work very well. I think anybody that's done AFM has been at that point of frustration. Again, I think it's useful to emphasize what actually is occurring in an AFM contact mode scan, and I try to illustrate that here in this picture. There's some surface feature that you're trying to obtain an image of. This surface feature could have a height that ranges from nanometers to microns. The way you want to image that surface feature is you want to move a tip across it. The tip is attached to a cantilever. You want to maintain a constant deflection of the cantilever. In doing that, you're going to be moving the relative distance between the tip and the substrate. So the cantilever signal, right, that's proportional to the deflection of the cantilever is essentially zero except at the points where the feature has a sharp step. And so the cantilever deflection is going to be non-zero in these two triangular regions that are indicated in the middle slide here, right? And on the basis of that information, you have to adjust the Z position of the sample in order to keep the tip sample force fixed. And so perhaps you're going to adjust the tip sample separation in such a way as indicated by the red diagram, the red line in this bottom diagram, and the hope is that that adjustment then matches to a fair approximation of the topography of the feature that you're trying to achieve. But the way that all occurs is by optimizing this feedback loop tuning parameters. You have to have good tuning parameters, or otherwise the image that you get of the object will not be a true image. So there's some empirical procedures for setting K sub P and K sub I. If you're interested in this, you can read it on your own. It's not worth my while actually reading through it step by step. This may give you some insight into the types of adjustments that are required if you're performing contact mode scans. And then lastly, I'd like to emphasize that once you've actually obtained an image, it's very important that you have some very good data processing software. This data processing software should be very versatile and allow you to analyze the images that you obtain in a very simple and easy way. And in particular, right, you're not only going to look at the images with a variety of software techniques, but you're going to be looking at profiles on those images to obtain detailed information about the heights and widths of certain features, Perhaps if you have a dynamic process, you want to achieve some sort of a movie of the dynamic process as it unfolds. And then lastly, there's always advanced features which different AFM manufacturers build into their software. So apart from acquiring the image, after the image is acquired, you have to have this capability to analyze it. This is very dependent on the company that makes the software, that writes the software, so we're not going to focus too much on it in this course because it's different for every AFM that you might want to use. So, if you successfully are able to capture contact mode scans using an atomic force microscope, if you develop this ability, then I think what you'll find is that there are many, many applications that you can use the atomic force microscope to study. And I just run through a short list of those applications right here. So the effort made to learn how to do a contact mode scan, in my opinion, is very worthwhile, because if you become a resident expert, you'll find that a lot of different groups around your research lab will be coming to you, asking you for help in either obtaining or interpreting data. So this is a good position to be in because it just increases your ability to learn new things. So the last topic in the third week is going to be a discussion about the atomic force microscope as a system. What I like to do in that lecture is try to convince you that it's worthwhile to think about in a holistic sense all the features that go into making an atomic force microscope work efficiently. And we'll discuss some of those features in the next lecture. So we'll see you then. Thanks.